And is the font big enough for you guys, or you want me to make it bigger? It's good? Okay. So we're going to start Unit 3. Up through Unit 3 will be on your test. So when we finish this, I will go through and tell you which stuff from Unit 3 you're going to want to focus on more for the test. And if we have time to go on to Unit 4 today, we will do that. And then before you go, remind me and I will talk to you about stuff for the lab for next week. We're going to be doing one of them on one of the evolution labs. We'll actually probably do both of them since they're little worksheets basically that you do at home. You don't need any supplies for them. So that way you can have the full 2 hours for your test if you would like it on the test day on Wednesday. So with water, this is going to continue the chemistry portion of things. It is going to be very familiar to life on Earth. All organisms are made mostly of water and live in an environment dominated by water. So when we talk about organisms, we're looking at life on Earth. Life on Earth is dominated by water, so that includes us in there. And on Earth, you'll find water in all three states as a liquid, a gas, or a solid. So the solid is ice, the gas is steam. And it will participate in reactions to sustain life. And it makes up the majority of cells, 70 to 95% of it. It's also going to surround cells. So if you were to cut open your body, even if you didn't cut open any blood vessels, it's going to be wet and juicy inside because there is a watery substance that is around all of your cells and tissues in there without it being blood. Water is a polar molecule, which means that where we talked about those polar covalent bonds where water didn't share electrons equally, all of the hydrogens tended to cluster their electrons on one side, so you had a partial negative charge occur as a result, and all of the oxygen on one side, all of the hydrogens on the other end were not able to pull electrons over there, so those would have a partial positive charge on that end. And that unequal distribution of the electrons is what's going to account for a lot of the properties that water has. So some of these properties, one of the things is it's got cohesion. It tends to hold itself together. When you spill water, it doesn't shatter and go all over the place. It sticks together in clumps like that. This is also going to be what allows it to move up against gravity in plants. So it will tend to adhere to surfaces. So let's say you get your hand wet. If you turn it over, the water doesn't all fall off. Like maybe if you put sand in your hand when you turn it over, the sand doesn't adhere to your hand unless you're sweaty. It just falls off. Water, on the other hand, is going to stick to it. You can go like this and you still have some of the water on there. That's what we mean by the adhesion in there. That also helps it to resist gravity, to be able to come up from the ground into the stems of plants in there. You've got surface tension of water, which is because of those water molecules sticking together. It's got surface tension that's greater than most things in there. That's what allows bugs to walk on the surface of water, is they are not heavier than what the force of that surface tension is holding it on there, so they can walk on there. Now you or I try it, we're a lot heavier than that bug and we're going to fall through it in there, but that's why they're able to do that. Another thing it likes to do is it helps to moderate temperature in there. It can absorb a lot of heat and it can also release a lot of heat with only a small change in its temperature. And where you can see this happen is if you look at places that are near water, near bodies of water, the temperature changes are not real extreme, like in the Puget Sound area versus the desert. So say you go out to the high desert even in eastern Washington you'd find it, but like say you go out to the desert in California, where like Joshua Tree is and things like that, in the winter months, it can drop down and be below freezing at night, and then you can still have it be 80 plus degrees during the day in there. That's a really wide change in the temperature, but there are no big bodies of water immediately close. You've got a mountain range between the ocean and that desert in there that allows that wide temperature range. Here, we know that if it was 15 degrees at night, we're not going to get very warm during the day. It's just not going to happen. But we also don't have a lot of time where we have extremely cold temperatures or extremely hot temperatures here. The Puget Sound and our proximity to the ocean really helps to absorb those changes. So it also is going to do that on a smaller level in a body as well. It's going to help us from having our body temperature change every time the outside environment around us changes. So that's what is meant by a heat bank. The kinetic energy is the energy of motion in there. So the faster something moves in there, the higher the kinetic energy. And heat is a way, it's a form of energy. It's a measure of the kinetic energy due to the motion of the molecules in there. So when we talk about measuring the heat of the water, what we're measuring is how much energy is in there with those water molecules moving around inside. And then temperature is a measure of the heat intensity. And that's going to be the average kinetic energy of it regardless of the volume in there. So heat and temperature, we tend to, in general terms, layman's non-scientific terms, we go, oh, the same thing. They're not. In the science world, one is going to be that total energy in there. And because the total energy in there and how much they move depends on the volume, heat's going to be based on that. Temperature is going to be irrelevant of the volume in there. So when we talk about the movement of heat, heat moves from the warmer object to the cooler object. So heat is going to be what moves, not the cold. So a lot of times people go, oh, you're letting the cold in. You're not really letting the cold in, you're letting the heat out. Because the things that are moving, they're looking for ways to be able to move faster and escape more. So when the doors open, they head out there, and then they've got a lot more space. The slow, cold molecules are not going to rush in the door here. So what we notice is what makes us uncomfortable, the cold. But if it was air conditioned in here, it isn't that you're letting the cold out. You notice that heat coming in. So the calorie is going to be the unit of heat, or the amount of heat it takes to raise the temperature of 1 gram of water by 1 degree Celsius. So with a lot of the metric units in there, it's kind of nice that they will look at things and it's 1 gram, 1 degree. They keep the units pretty like that, which makes it a little bit easier to work with. So the kilocalorie is 1,000 calories, so that's to raise 1 kilogram of water by 1 degree Celsius. And actually, when we are looking at things on food, it will say calories, but what we're actually looking at is kilocalories. It's just an easier number to work with, and if you put kilo in front of something, it tends to just confuse the general population. So that's why your food labels are going to say calories in there. So joules are also an energy unit. 1 joule is 0.239 calories, or 1 calorie is 4.184 joules. So if you look at food labels outside the United States where they use the metric system, you'll see they'll not use calories on there, they'll use joules instead. So to me it seems a little bit odd that, we talk about everything else being, we'll talk about how many ounces of food you have in a container, and then you get calories, and then we talk about how many grams of carbohydrates and fats we have in there. The metric system is easing its way in. It's just, we make things more complicated for ourselves by going between two systems like that. So the specific heat is going to be looking at the amount of heat that is absorbed or lost to actually change the substance by 1 degree Celsius. 1 gram of the substance by 1 degree Celsius. Water has a high specific heat, which just basically means it's hard to change the temperature of water. It takes a lot of energy to do that. Part of the reason it takes a lot of energy to do that is all those hydrogen bonds in there. So one of the things you're going to want to do for your test is I would take all of these heat terms, you're going to look at them in here, and you're going to heat, temperature, specific heat, they're all going to look the same. What I would do is take those terms that look the same, put them on a little card in there, and study that stuff together. Don't do anything else when you do it, and just kind of beat the difference in the definitions into your head in there. That's the way I'm going to look at it, is say, okay, amount of heat that it takes to heat or amount of energy lost to change the temperature by 1 degree Celsius in there like that. Yeah. No. That's what you get math classes for. Yeah, if for some reason you're going to have to calculate something in here, I'll give you fair warning and say here is some things to practice on. Like you had with the scientific notation, there were those to practice on. But there's been nothing that you've needed to actually calculate in here with this. And in biology, nursing and things like that, you're not going to be ever calculating that stuff. So just to give you a comparison, water specific heat is 1 calorie per gram per degree Celsius. Alcohol, we know that alcohol evaporates a lot easier. Part of the reason it does is its specific heat is only 0.6 calories per gram per degree Celsius. So if you were looking to cook the liquid off of something, you can cook the liquid off of alcohol a lot easier than you can of water. So maybe you're cooking something, you know, a sauce of some sort, and one of the things that they'll do with certain sauces is they make reductions where if you cook with wine, they talk about reducing it. And wine, if you you're boiling wine, the volume of it's going to go down a lot faster than it is with water because the alcohol in there will evaporate off real quickly. That's also why you're not going to get drunk off of cooking with wine, is you're going to cook the alcohol off of it, and what's left is the other stuff in there for the flavoring. So with evaporative cooling, the molecule moves fast enough in there to escape and depart the liquid. So when something is evaporating, you put enough heat in there and it's jumping up and down high enough that it finally just gets to leave. And when it leaves, it takes some of the energy with it, and that's why you have the cooling of what is left behind. So when you sweat, what's happening is you've heated up that moisture on your skin enough that a molecule gets to leave in there. When it does, it takes some energy and it leaves the temperature behind lower, and that's what cools you off. So if you are sweating and you're just drenched with fluid and it's not going anywhere off your body, that's not very effective at cooling you off. Where if it is able to be evaporating and leave, that's why it's going to be much more effective at cooling you. And that's the idea. If you go into the mountains at all or anything, people will say, you know, don't wear cotton. Cotton kills out there because it doesn't allow the liquid to evaporate off of there. It's going to hold it against your skin. So if you're hot, it's not going to allow you to cool real effectively. Also, if you're too cold, then you've got that against you there. That's also going to make it inefficient for you to regulate your body temperature in there. That's the idea between those fibers that move the liquid away from your skin faster. So the specific heat of water is 10 times that of iron. So one of the things you notice is your pot will get hot before the water in it does, because it takes a lot less energy to heat up that pot than it does the water. So the pot gets hot before the water does. So you may touch the outside of the pot and go, oh yeah, the water should be hot in there. No, not necessarily. What's in it might still be cooler like that. And that's part of the reason it takes so long to cook certain things in there. So the heat of vaporization is the quantity of heat that a liquid must absorb for 1 gram of it to be converted into gas from the liquid state. So to evaporate 1 gram of water at 25 degrees Celsius, it takes 580 calories of heat, which is nearly double the amount it would take for alcohol or ammonia. Hence, those things evaporate much easier. So is that idea kind of making sense to you guys in there? What happens with the water? I know the terms of it can be kind of boggling in there, but as long as the big picture is making sense when we're going through it, that's the important thing. So insulation of a body of water. Water also tends to kind of insulate itself. Ice floats on water, and at temperatures above 4 degrees Celsius, it actually expands as it warms and as it falls towards 0 degrees. So water is the most dense at 4 degrees Celsius. So that's when it's going to be the most likely to sink. So if you've got water that's 4 degrees Celsius and then you've got some that is 0 degrees Celsius, the 0 degrees Celsius is less dense, and that's why it's going to float on there. And that ice will actually then create a barrier that kind of insulates what's underneath. Yeah. The what never overflows? Right, because it's going to be less dense than the water is underneath it. So when it gets to the normal temperature in there, you actually have a lower volume in there with it. So water is a really common solvent in there. So it's going to dissolve a lot of things. A solution is just the liquid that is a completely homogeneous state or mix of 2 or more substances. So with it being homogeneous, it means you can't separate it anymore. It's completely blended. The solvent is going to be the dissolving agent, and the solute is the solid agent that dissolves or dissociates. So we call it an aqueous solution when we use water as a solvent. It's got its own name because it is such a common solvent in there. So we have a hydration shell, which is a sphere of water molecules around a dissolved ion. So when you put that ion in there, you have the partial positive and negative charges of the water that wrap around that ion in there. That's what allows that ion to fit in between the water molecules. So you've probably heard, okay, this when you put salt into water, the salt's going in between the water. What's happening is the water molecules wrap themselves around those ions like that, where you've got the positives and negatives attaching to the partial positives and negatives in there. And it's just referred to as a hydration shell. So when something is hydrophilic, it has an affinity for water or it likes water. So like where you say a pedophile really likes children, hydrophile really likes water. Hydrophobic repels the substance in there. So if you have a phobia, you're afraid of something, you don't like it. And then colloids are kind of a weird thing. It's a stable suspension of fine particles. It's not completely dissolved in there. You can actually see the particles floating around in there. But it's stable. It's not like they're going to settle out to the bottom. So why would we need to know solute concentrations? When you look at chemical reactions, you need to know how many atoms and molecules you have to calculate the concentrations. So just like if you're going to make a double batch of cookies, you know you need to double every ingredient in there. You don't just double the flour so that there's more bulk of it. You'll have to double everything that interacts with it. It's the same thing that we're looking at with chemical reactions. If you're going to make twice as much of something, you need to make sure you have twice as much of all of the atoms and molecules that are going to be in there. And we use the mass to calculate how much we need in the experiment, but we actually use this concept of moles in there to figure out how much we need in terms of the proportions. So is anybody in here familiar with the concept of a mole? So these are not the little guys that live in the ground.
Would you care to explain?
So just like when you say you have a dozen of something, you know that means 12. When we say we have a mole of something, we mean we have 6.02 times 10 to the 23rd of something. A whole lot more of it. So if you said, okay, for this recipe you need a dozen eggs, if you're going to make a triple batch of that recipe, you need 3 dozen eggs. When we look at calculating it out in chemistry, we could say, okay, for this one you need 1 mole of this to react with 2 moles of this. If you're going to double it, you need 2 moles to react with 4 moles in there. Does that kind of make sense, that idea in there? That it's like saying another unit, and this is just a really big unit in there. So when you look at the periodic table, you can look at your molecular mass or molar mass, and that's going to be the sum of all the masses in the atom or a molecule. So when you're looking on there and it says your atomic weight, we talked about where you find that on your periodic table, which reminds me, I copied some periodic tables to give you. I'll be right back. Okay, now we don't have to try and read the one that's behind the post. So when you look on here, you can see up at the top of the little square, you've got the atomic number. And then down at the bottom in a decimal point, it's going to have your mass in there. So that's telling you the mass of one atom on there in AMUs, but it also tells you the mass of 1 mole of those in grams. So as you move down the periodic table, 1 atom of carbon weighs more than 1 atom of hydrogen. So when you are looking at carbon and hydrogen together, in methane here, the CH4, what we do is we add all those things together. So carbon's got a mass of 12, and it's a decimal point on there, but we're rounding to keep this math easy on here. Hydrogen of 1, there's 4 hydrogens, so it becomes 4 plus 1. Yeah, the one that has the decimal points on it. So the mass of the methane is 16. So when we calculate the ratios of things interacting together, we need to know how many atoms, and because atoms are so small, we talk about it in terms of moles. But if we actually need to be able to measure it, then we have to convert it into grams, and that's how we do it. The other one's the atomic number. So the atomic number explains how it behaves. The mass is the size of it, or the amount of it in one atom. So I know that that's kind of an odd thing to look at right now, and you're probably going, oh God, what did I just get myself into here? So that number on the bottom, numerically, is the mass of one atom in atomic mass units. That same number is the mass of 1 mole of the substance, only it's in grams. And 1 mole of the substance is the 6.02 times 10 to the 23rd units of something. So if I were to ask how many atoms are in 1 mole of neon, 6.02 times 10 to the 23rd. How many atoms are in 1 mole of uranium, 6.02 times 10 to the 23rd? How many ants are in a mole of ants, 6.02 times 10 to the 23rd? So a mole of something is always that many, just like a dozen of something is always 12. So that makes sense in there. There is calculations for it where they actually were able to measure the mass of something, and then they looked and they knew the diameter of it and the size, and they calculated it out. No, for the high school class, I have a sheet that shows all the calculation of how they figured out that number. I can't say I've ever had to use it for anything other than keeping teenagers busy. And that's all it does, is it keeps them busy with that. So, and Avogadro is the one who came up with that number in there. So when we talk about molarity, it's the number of moles per solute per liter of solution. So it's how many moles are in 1 liter of a solution. So when you're looking at making a solution in there, sometimes it may give you how many grams per liter in there. You may look at it that way. Or if they're talking about the molarity, they're talking about how many moles are in there. You could figure out how many grams are in there if you know that you have 2 liters of a solution in there. You figure out the moles, and then you can convert it into grams. You're not going to need to do that in here. So it's just knowing the idea that we can talk about it in terms of moles. And if you're having to figure things out in chemistry, you always go back to the mole and then figure out the masses from there. The mole is kind of the universal comparison. Instead of saying, well, we know we have 1 atom of this reacting with 3 atoms of this, reacting with 4 atoms of this, we say 1 mole because the atom is so small and microscopic you can't see it, where the mole is an actual tangible mass for a lot of things.
I see a small discrepancy here with these figures of the Avogadro's number. It illustrates here on my chart 6.023 pi by 10 to the 23rd power. Is this like kind of off or something? Or?
It's just more significant digits in there. It's a more accurate number in there. That's a rounded number. So yeah, you could actually go beyond that in there, but usually in your calculations that you're going to do, if you are looking way out there at those digits down the line, and you're talking about, it's kind of like if you're talking about trillions, and you're trillions of dollars, and you're arguing about the pennies, and there, it's kind of like, who really cares about the pennies? It's not significant. So that's the reason we round that one. So the acids and bases in living organisms. I just want to see kind of where we are in the notes of this. Why don't we take a couple minutes after this mole thing here? If you guys need to run to the bathroom or something like that, just pause this. Oh, shit. I was good today. I did pause this. Oh, shit. I was good today. I didn't mumble any swearing to myself up here into this microphone. That's why I don't really like the idea of having to wear this headset with the microphone. So if you're hearing my recordings and I trip on something or stumble up here and you hear some swearing, I apologize. It just comes out without me thinking. So you already have the list of what to study for the Chapter 1 and Chapter 2. For Chapter 3, where you want to focus your energy is on the section on the moderation of temperature, the insulation of a body of water, solvent of life, solute concentrations in chemical reactions. What was that one again? Solute concentrations in chemical reactions. And effects of changes in the pH. So I was making notes of what to tell you to study as I was making your test. Effects of changes in pH. So what your thing is actually going to look like is one page. There's matching on there, which I know you can't read any of it. And that's kind of the idea of me standing up here.
That's okay.
Yeah. So with the matching, I use the keywords for the definition in there. So your key points to match up in there. There's a few multiple choice and a few fill in the blank. As you can see, there's no room to do any calculations on there. Like more, like
blah blah blah, and make our answer, or
yeah, you don't have to use a complete sentence.
okay, but well, maybe it would be like, can you give an example of this type of thing, or
So if I were to say, what is something that absorbs a pH change? You could say that. They're pretty short answer like that. So I think what I put on that list pretty much covers what you need to study with it, though. So you'll have the entire time to go over it in there. Yeah. So we'll go ahead and get started on Unit 4 then. This is everything that we're starting from this point on would be material for the second test. So I'm not rewriting that thing. That's one thing I actually have completed on my list is your first test. Okay. So I apologize, there's going to be a big blank spot in the video here where I thought I paused it and I didn't. So Unit 4 is going to be looking at carbon and the molecular diversity. So we're going to start to look at some of the bigger atoms in here, getting more involved with the ones that are associated with life. So one thing with carbon is all life forms on Earth of life as we know it is mostly made up of carbon. So organic chemistry is the study of carbon compounds, and that branch of chemistry specializes in just studying the carbon compounds in there. So if you were to go in and go to a university to study things and go on like that, you would take a year, for just about any science degree, you'd take a year of biology, which this class is the first quarter in that year. You'd take a year of general chemistry and a year of organic chemistry. So this idea of vitalism is a belief in a life force outside the jurisdiction of physical and chemical laws. Years ago, this idea of vitalism was the foundation for this new discipline of organic chemistry. And as they started to understand things, this vitalism kind of got chipped away at as they started to be able to make organic compounds in the lab. So the first thing they learned to do was how to make urea without a kidney. So kind of almost a synthetic urine. And then they kind of decided, okay, this stuff doesn't require something that's alive to make it in there, and that kind of chipped away at that idea. Kind of funny to think that making fake urine would have such a profound effect on science. So mechanism is the view that the physical and chemical laws govern all natural phenomena, including life processes, and that's kind of been the shift in science. Instead of saying, well, these are the things we can explain through science, and then these are the magic things that living things make, now we've been able to make those compounds as well, and it's become more mechanistic in its approach to things. So because carbon has those 4 bonds that it will form, those 4 valence electrons, it's going to form diverse molecules that will go into those 4 slots. So carbon structure, it's got a total of 6 electrons. You put 2 in that first shell and 4 in the second shell. So because that second shell has 4 in there, it leaves 4 empty spots. It's got the 4 valence electrons and can form 4 covalent bonds so that it has the access to 8 electrons. Leash doesn't allow me to get to an eraser. Yes, think carefully about what you draw. So basically, organic chemistry is studying what goes on these slots there with the 4 valent electrons. So the naming in organic chemistry, some people think it's more complex than general chemistry. I don't think it's necessarily too bad. The names of things have to do with the number of carbons in there. So when you have 1 carbon in there, it's going to have meth in its name, and not like tweaker meth. If it's got 2, eth, 3 is prop, 4 is bute. And the easiest way to remember it is you just memorize that little meth, eth, prop, bute word in there, and it's 1, 2, 3, 4. So if you see something that says Methanol, you know it's got one carbon. So the ending, ANE, means it's got single bonds in it. ENE means it's got double bonds in it. And the YNE means it's got triple bonds in it. So you don't see methene, you see methane, because if this had hydrogens here, we've got one carbon, it's all single bonds, methane in there. Now, if you've got a double bond in there, and you've got two carbons, what are we going to call that one? We know where your mind is. The OL ending is alcohol. So you've got two carbons, eth, double bonds, ethene in there. So it's pretty easy like that. If we had a triple bond, still no alcohol in it yet, Dominic. So that would be ethyne in there. You've got the INE ending in there. So it does make it a little easier to figure out what you're looking at in there. If you can look at it, and you will, if you look at anything that's got organic stuff in it on a label, they become a lot less mysterious to you when you can look at the endings and go, okay, I know what that means in there. I know what this means. And so with the sugars, like with glucose in there, it means you've got 6 carbons in the sugar in there. A pentose in there is going to have 5. So it takes a lot of the mystery out of the names in there. So carbon chains are going to form the skeleton of most organic compounds. They can vary in length in there. They can be straight or branched. They can be in rings. The number of bonds can vary, and the additional elements that bond to it can vary in there. So hydrocarbons are going to be things that consist mostly or only of hydrogen and carbon in there. So a lot of your fossil fuels, when they talk about burning hydrocarbons, what they're talking about is building things that are mostly carbon and hydrogen. So if we say propane, most people have heard of propane. You recognize it as a gas. 3 carbons, because it's prop, ANE ending. That's exactly what you have from it. So it's pretty easy to figure out some of those simple names in there with that. So when you're lighting up your barbecue, that is what you're cooking in there. So see, I did propane, not that bad. When you're walking by the cow, that's what you're smelling, methane. So a major component of petroleum products is going to be hydrocarbons, and because they're partially decomposed but not prevalent in living organisms, you're going to find this in, they're going to have these in a lot of regions. So what has made your fossil fuels, and the reason they're called fossil fuels, is because they're made of partially decomposed organisms. Organisms are made from carbons, and that's how we get all of the carbon in that fuel in there. So they're hydrophobic. They do not like water. If you look at this and you think, okay, we're sharing electrons in there, everything is equal all the way around. It's as symmetrical as it gets. It does not have a place where it's going to share unequally. And water likes to have other things that are going to have charges or share things unequally. So it says, you know what, you're an equal sharer. We don't want to play with you in there. They undergo reactions that release relatively large amounts of energy. So when you burn these, they release quite a bit of heat. Hence, you use this for your barbecue. So when we have isomers, it's a variation in the architecture of organic molecules. So a structural isomer is going to differ in the covalent arrangement of the atoms. So with this one, there's not too much you can do to alter the variation of that. But you can have it be a difference where maybe instead of it being the carbon being over here, you could have the carbon here and a hydrogen here. And then this one having the 3, where it will have a bend in it like that. So a lot of times when you see iso in the name of something, it means it's an isomer of it where it's just arranged slightly different. A geometric isomer is going to have the same covalent partners, but they're in a special, different spatial arrangement in there. And they'll be referred to as cis or trans. So let's say on here, with this one, we're going to put a fluorine on there instead. So right now, this one we would say is cis because the 2 fluorines are next to each other. If we arrange it like this, now it's trans because they're opposite of each other. So could you think of something you've seen in food where this cis and trans has come up? Trans fats. So what they're talking about is fats that do this kind of arrangement instead of this artificially in there. That's what's meant by it, is instead of them being next to each other, now they're like this in there with cis and trans in there. And then we can have enantiomers, which are isomers that are mirror images. So the middle carbon is going to be its asymmetrical base, and in order for it to be an enantiomer, there has to be 4 different things on it. And we refer to them as like a left and right-handed version of it. And so it refers to how it spins light that is put through it. So one is usually biologically active, and one is inactive. And so with a drug, the enantiomers may not be equally effective. And an example of this was thalidomide, which was used for morning sickness years ago, and it ended up causing a lot of other problems for people. So the good enantiomer had the desired effect. The other enantiomer was harmful. So what had happened is you would purify it, and the patient would take all of one form, but when it went into their body, half of it would switch to the other form in there, and that's where you had the problems with it. So what they were taking wasn't actually toxic, but their body converted it to the toxic enantiomer in there. So if you think of the enantiomer as the right and left-handed version of a molecule in there. So the chemical groups that are on there are going to be key to the functional biological properties of molecules. And the functional groups are going to be the chemical groups that are going to replace one or more of the hydrogens. So these hydrogens, where you have these bonds, you could stick some other functional group in there and make something else in there. And these are going to be 7 functional groups that you're going to see in biology in here. A lot of how it's going to participate in a reaction is going to be based on the functional groups in there. So if somebody is going to build a molecule and you say, well, you know what, I want some of these properties of the amines on here, but I also want some of the sulfur properties in there, you can actually build molecules by picking and choosing. It's kind of like saying, you know what, I want to make this meal, and I'm going to go to the store and pick the ingredients that I want. So in organic chemistry, your first quarter you're learning all the names and stuff like that, and your next 2 quarters you start learning reactions on how to build and glue these things on and how to take them off and convert them into other things. And that's what you spend the rest of that class doing, is creating the reactions to build different things or how to take them apart. So your hydroxyl group is going to have your OH on here, And so the chemical group is the name of it. Your structure is right here. This is what makes the alcohols. So with your ethanol in there, one of the things that it gets attached to it is a hydroxide in there, and that's how it gets the name in there. Still has 2 carbons. That's how the name comes up. So these are used to make a molecule polar. It's going to form hydrogen bonds with water, and it will help to absorb or dissolve organic compounds. So say you're making a drug and you want it to be water soluble. This could be something you could try and put on there that, provided it's not too big and has other things that are not water soluble, could help make it water soluble. The carboxyl, what that little arrow indicates on there is that kind of a bond in there. Or the carbonyl, I'm sorry, is that kind of a bond on there. This is going to be your ketones when they're found within the carbon skeleton. So if it's still built into the rest of it, if it's on the end, we call it an aldehyde. So some examples: formaldehyde in there. Ketone would be an example, acetone, and there would be a small one. So that's where that ONE ending comes from on those. So a lot of these are going to be your aldose and ketose sugars in biology. The carboxyl, this is your acid group on the end. So when you see an amino acid, it's going to have a COOH on there. That's why it's called amino acid in there. So your carboxylic acids are organic acids. Acetic acid or vinegar is going to have that group on it in there. So a lot of times when people kind of think, oh, acid bad, when you think, okay, acetic acid, vinegar, most people don't look and think vinegar is a bad thing. So this will give you a lot of the acidic properties, and it's found in cells. The amine group is this NH2 on here. So it gets named amino on there. So this is what's on your amino acids, is you've got this on one of the carbon legs, and you've got this on the other carbon leg on here. So an example of an amino acid would be glycine. There's lots of other ones out there. It can act as a base, and it can be ionized with a +1 charge under cellular conditions in there. So the sulfhydryl group, these are ones that have sulfurs in them, and so thiols are going to be the names of the sulfur compounds. So when you're looking on the ingredients of something and you see thiol in there, it means it's a sulfur compound. So cysteine is one of them. It's one of the amino acids, and so cysteine is going to be one, if you've got musculoskeletal injuries, can be helpful in having adequate amounts of that amino acid in there because of the sulfhydryl groups in there. It's also what's going to determine curliness or straightness of hair, and there's sulfhydryl groups. So if you were around in the 80s, and if you weren't, just keep your hand down and don't remind those of us that were how old we are. You probably remember getting your hair permed. Anybody in here get that done? You and I cannot be the only 2 people in this room to have gotten a perm. We know you must have at some time, Steve, with a mullet in there. You're my age, you know what perms were. If you remember, they stink. And what makes perms stink is the thiols. Also, what makes skunk stink? The thiols in there. And the thiols can be really hard to get rid of. I've had that experience with the skunk thing fairly recently. Phosphates in there, so that's that PO4 2- in there, your organic phosphate, glycerol phosphate. It will contribute to the negative charge of molecules. It's got the potential to react with water and release energy. So one of the ways you get energy from ATP, your energy currency in the body, is it reacts with water. So methyl groups, the CH3. So not only do we call this thing methane, if we take this off so we can attach it to another carbon in there, it's a methyl group in there. So this can be involved in methylated compounds. An example, 5-methylcitidine. It's going to affect gene expression. It can also affect the shape and function of sex organs in there. So with gene expression, one of the ways that the body can mark down and say, have I read this or corrected it, is it will stick a methyl group on the gene in there. It's also one of the ways that you can help protect yourself from viruses is you don't put methyls on those. So if there's no methyls on there, the body can look and say, you know what, that genetic stuff in there doesn't belong to me. It must have come from a virus, and help it to know when to destroy it in there. So ATP, your adenosine triphosphate, it's an organic adenosine molecule attached to a string of 3 phosphates. And this is going to be used to store energy in the cell. It will react with water to split off the phosphate in there. So that's going to be a good place to stop today. So even though it's a little bit early, I think that is enough information to swallow